So we have this pictorial representation of the second law, which tells us what kinds of devices are not possible to build. We cannot build a Clausius violator, a device which transfers heat from a cold place to a hot place without requiring work, and we cannot build a device which interacts with a single reservoir and produces net work over the cycle. Okay? A heat engine has to interact with two reservoirs. You take heat from a high temperature reservoir and dump some of that heat into a low temperature reservoir to produce work. So these are engineering statements about what kinds of devices are possible to build. Now, what implication does this really have as engineers in training? If you're an engineer who's going to be working at General Motors or Ford or Jaguar, you're interested in if there is a theoretical limit to the efficiency of an internal combustion engine that you design. What's the maximum possible efficiency of your new 12-cylinder Jaguar engine according to the laws of thermodynamics? I'll tell you what, it's not 100%. An internal combustion engine cannot take all the energy provided in the form of heat and convert it into usable work. It's not 100%. It's some other value. So what's the value of the maximum efficiency for your internal combustion engine? Likewise, if you're working for Hotpoint or Amana or GE and you're designing and building refrigerators, what's the maximum coefficient of performance for a theoretical refrigerator operating between a freezer temperature, T low, and a room temperature, kitchen temperature, T high? It's not infinite. You cannot extract out heat from somewhere cold without providing work to do it. Okay? So we're interested in getting a grip on what the maximum values are for efficiency of a heat engine and coefficients of performance for a refrigerator or heat pump. We're trying to get a grip on the numerical values of those quantities. How efficient is the most efficient engine you can possibly build? What's the coefficient of performance for the best heat pump or refrigerator it is possible to build? Thermodynamics can give you the answer to these questions, okay? So let's look at the limits. Let's calculate or get a grip on the limits. The upper limit on efficiency and coefficient of performance for any heat pump or heat engine or refrigerator. Let's get a grip on what these numerical values are. Well, let's start off with the following. Let's say we have a high temperature reservoir, TH, and a low temperature reservoir, TL. These are constant temperature sources or sinks of heat. Now, I have a heat engine right over here. So here's a heat engine, and it's working in a cycle. Now, this heat engine receives a certain amount of heat, QH heat engine. It takes some of that heat and produces work. And the remaining energy, what's left over, it rejects to the low temperature reservoir, QL heat engine. Now, I am going to take a heat engine which can be reversed, a reversible heat engine, and I'm going to put it side by side with my heat engine. What do I mean by reversible heat engine? I mean that this new reversible heat engine doesn't contain any friction, unrestrained expansion, or heat transfer across a finite temperature difference. None of those irreversible processes that we discussed in the last class are present associated with the operation of this reversible heat engine. It basically means in practice that I can run this heat engine and then I can reverse everything and run it as an equivalent heat pump or refrigerator. You'll see this in just a minute. So this reversible heat engine takes a certain amount of heat, QH, reversible, rejects, and by the way, I'm going to make this reversible heat engine, I'm going to make it bigger or smaller in size, so that the amount of heat rejected by the reversible heat engine is numerically equivalent to what's being rejected by our regular heat engine. And this regular heat engine may or may not contain irreversible processes, friction, unrestrained expansion, heat transfer across a finite temperature difference. I have not said that this is reversible. It's just a plain heat engine. But this guy is reversible, and I've made it big or small so that the heat rejected to the low temperature reservoir is exactly equal to that being rejected by our regular non-reversible heat engine. Let me get my notation right. QL heat engine. So I've changed the size of my reversible heat engine, made it bigger or smaller, until the heat rejected by the reversible heat engine is numerically equivalent to being rejected by the regular heat engine. Now, of course, this thing is producing a certain amount of work. It's a cyclic device. So this is producing a certain amount of work, and this is our reversible heat engine, okay? So hopefully you have the picture here. Two heat engines. One may or may not be reversible. It may be irreversible, contain friction, unrestrained expansion, heat transfer across a finite temperature difference. Then I have a reversible heat engine, which doesn't contain any irreversibility. No friction, no unrestrained expansion. We'll apply those in more detail later. No friction, no unrestrained expansion, no heat transfer across a finite temperature difference. So we have a reversible heat engine, okay? So this is the situation here. Two different heat engines, fine. Now, because this is a reversible heat engine, I'm going to reverse it. Reversible heat engine. So that means all the signs, all the arrows get flipped here. Flips, signs, and direction of heat transfer and works. Okay, when you reverse it, all the signs flip and the arrows flip in terms of the energy transfer. So let's write what we have here. Let's see what we got. So here's our T high, and here's our T low. So we have our reverse heat engine, which is now a heat pump or refrigerator. I'm just going to write it as rev heat engine, and I'm going to write right below it in parentheses, reversed. So I'm reversing my reversible heat engine. So now it's taking QL reversible, which by the way is equal to QL for my heat engine. It's taking heat from the low temperature reservoir, shoving the heat, and then some, shoving the heat up to the high temperature reservoir and then some, and is receiving a certain amount of work. Work reversible. Okay? So the thing is a reversed heat engine or a refrigerator or heat pump receiving W reversible to transfer heat QL from the low temp to the high temperature reservoir. Let me put in my regular heat engine, which is to the right. So here's my regular heat engine. It's working in a cycle. These are all working in a cycle. So this guy received QH, heat transfer from the high temperature reservoir, rejected some heat QL to the low temperature reservoir, producing a certain amount of work. Now here's the key. I'm going to take some of the work produced by the heat engine to drive the reversible heat engine. Okay? So I'm going to subtract off the work produced from the work produced by the heat engine. I'm going to subtract off the work consumed by the reversed heat engine, and I will get a W net. A net work. What is this net work? It's equal to the old work produced by the heat engine minus W reversed. So the net energy or work, the net work produced by the heat engine, some of the work is produced to drive the reversible heat engine. The net is the work produced by the heat engine minus that consumed to drive the reversible heat engine. Now, let's draw a control volume around this composite device. Let's draw a control volume around the composite device. And let's write what we've got. So here's our composite device. And here is our low temperature reservoir. So I have my reversed heat engine, reversible heat engine, plus my regular heat engine, okay? Now, the net power produced by this thing, W net, is equal to W heat engine minus that used to run the reversed heat engine, reversible heat engine. So W reversible. That's the net power produced. And the net heat transfer. The net heat transfer is, let's go back here and look at it. The net heat transfer is Q high heat engine minus Q high reversible. So the net heat transfer from the high temperature reservoir into our composite device is Q high heat engine minus Q high for the reversible heat engine, okay? So that's my net heat transfer from the high temperature reservoir. What's my net heat transfer to the low temperature reservoir? What's the net heat transfer? Well, I have QL from the heat engine being rejected to the low temperature reservoir, but I have equal and opposite amounts of heat being extracted from the low temperature reservoir to power my reversible heat engine. So the rejection from the heat engine gets canceled out by the extraction from the reversible heat engine, and there's no heat transfer to the low temperature reservoir. So it's as if there's no low temp reservoir in this equivalent situation, okay? Now, let's look at three different possibilities here. Let's look at three different possibilities. Possible cases. Case one. The work produced by the heat engine is less than the work produced by the reversible heat engine. I guess I'll write reversible heat engine here, okay? In other words, the heat engine produces less work than the reversible heat engine, so the efficiency of the heat engine is less than the efficiency of the reversible heat engine. So work by the heat engine is less than that of the reversible heat engine, which implies eta for the heat engine. The efficiency of the heat engine is less than the efficiency of the reversible heat engine. Okay, so that's possibility number one. Let's see what that looks like. If the heat engine produces less work than the reversible heat engine, then the net work is negative. This thing isn't producing work, it's consuming work. So energy in the form of work goes into the system, and that energy gets rejected to a single reservoir. So the picture here is of our device, work going in, heat going in to the high temperature reservoir. That's the picture. That picture, according to the Clausius Kelvin-Planck statement of the second law, is possible. The Kelvin-Planck statement says that a system interacting with a single reservoir cannot produce work. This is consuming work. We're doing work on the system, and it's rejecting that work in the form of heat to the reservoir. That's possible according to the Kelvin-Planck statement. Possible via Kelvin-Planck statement. So according to the second law of thermodynamics, it is possible for the heat engine to have a lower efficiency than the reversible heat engine. That is possible. Let's look at possible case number two. W heat engine is equal to W reversible heat engine. The reversible and the regular heat engine produce the same amount of work. That means W net is equal to 0. This device works in a cycle. It produces no work over the cycle. Therefore, it cannot extract any heat over the cycle. So this implies the works are the same. This means the efficiencies are the same. The reversible heat engine and the heat engine have the same efficiencies. And the picture here is work equals 0, Q high equals 0. Here's our high temperature reservoir. In this case, the system produces or consumes no work, therefore rejects no heat, therefore it does nothing. This is possible according to the Kelvin-Planck statement. The Kelvin-Planck statement simply says that this device cannot produce work over the cycle. It doesn't say it can't consume it or it can't do nothing. It can do nothing, it can consume work, but it cannot produce it. Let's go to our final statement or final case. Let's say that the work of the heat engine, we first asked what the case state of affairs was. It would produce less heat than the reversible, less work than the reversible, equal work. The only remaining case is the heat engine produces more work than the reversible heat engine. W heat engine greater than W reversible heat engine. So that's the third possible state of affairs. The heat engine produces more work than the reversible heat engine. Now that implies eta heat engine greater than eta reversible heat engine. That implies that the efficiency of the heat engine is greater than the reversible heat engine. If that's true, if this is greater than this, then W net is positive. The device produces work. So the picture here is a device that produces net work. That's what case 3 implies. W heat over the cycle for the heat engine is greater than the work for the reversible heat engine. Therefore, the net work is positive. Therefore, this guy interacts with a single reservoir and produces net work. That is a violation of the Kelvin-Planck statement of the second law. Not possible via KP statement. Not possible. What do we conclude? What do we conclude? We conclude that the maximum possible efficiency of any heat engine, conclusion, the maximum possible heat efficiency of any heat engine is equal to the efficiency of the reversible heat engine. Eta max is equal to eta reversible. By the way, I haven't proved it, but it's also true. COP max could be for a refrigerator, could be for a heat pump, who cares? COP max is equal to the coefficient of performance for a reversible refrigerator or heat pump. So the upper bound on the efficiency of any device, heat pump, refrigerator, heat engine, is equal to that for a device that operates reversibly. No friction, no unrestrained expansion, no heat transfer across a finite temperature difference. Box this up. Very important results. Very important results. Okay, so simply by drawing pictures and using control volumes, Along with the second law of thermodynamics, we're actually starting to get numbers. We've got upper bounds on the efficiency of a heat engine, heat pump, or a refrigerator. Now, let's see if we can get a little bit more mileage out of this. A little bit more mileage. Let me write down the actual expressions for efficiency and coefficient of performance for a device operating between two reservoirs. So here we have our T high. Here we have our T low, and we have a general device here. Let's say it's a reversible device. Could be a reversible heat engine, could be a heat pump, could be a refrigerator. I don't care, okay? So it's either consuming or producing work over the cycle, either rejecting or extracting QH over the cycle and rejecting or extracting QL over the cycle, okay? So it's a general reversible device, heat pump, heat engine, or refrigerator. Let's see here the efficiency for this reversible heat engine. That's going to be equal to the cycle work over QH. If you apply the energy balance to the reversible device over the cycle, you'll find that QH, you'll find that the cycle work, W cycle, is QH minus QL. So you'll have 1 minus QL over QH. And remember, this is for a reversible. Reversible device or process. Reversible process. Okay? Again, work cycle is QH minus QL. Okay, do a little cancellation. 1 minus QL over QH. COP, let's say for a refrigerator. The benefit for a refrigerator, what we're trying to do is transfer heat from the low temperature reservoir, and we must apply work over the cycle to do it. Work cycle is Q high minus Q low. And so we get 1 over QH over QL minus 1. And this is a reversible device or a reversible process. Okay. What about for the heat pump? Heat pump, the idea is how much heat is being rejected to the high temperature reservoir. And of course, the cost is the work over the cycle. The work over the cycle is Q high minus QL. Again, surround this with a control volume. Delta E over the cycle is 0. You get work is equal to Q high minus QL. Okay? And that gives us 1 over 1 minus QL over Q high for the reversible device or process. Okay? So all these coefficients of performance and efficiency have one thing in common. They have the ratios of the heat transfer, either QL over QH or QH over QL for the reversible process. They all involve a ratio of heat transfers. If this were a continuously running device, this would be W dot, QH dot, QL dot for a continuously running device. And these would all have dots on top of it, okay? But the idea is still the same. The ratio of the heat transfers for a reversible process appears in all the expressions for efficiency and COP for the device, okay? What is the relationship or the ratio of QL over QH for a reversible process? I'm going to state without proof. Going to state without proof the result here. Very simple expression for the ratio of heat transfers for a reversible process. It's simply the ratio of the temperatures for the reservoirs. So here we have a high temperature reservoir. Here we have a low temperature reservoir, and we have some kind of a device, a cyclic device. Could be a heat engine, could be a refrigerator. Reversible, work cycle. The ratio of the heat transfers, QL over QH for a reversible process, a device that operates reversibly, is equal to the temperature ratio of the associated reservoirs, TL over TH. Ratio of the heat transfers is equal to the ratio of the temperatures. By the way, again, as I just said a moment ago, this also works for a continuously running device. So I can also say Q dot L over Q dot H for a continuously running reversible device is also equal to TL over TH. So if you want to write that right over here, that's just fine with me. Put a box around these. Very important result. Very important result. Two things to note here. If you flip this, QH over QL for a reversible process is equal to TH over TL. Q dot H over Q dot L is equal to TH over TL for a reversible process. So you can take the reciprocal and it also applies. One other little thing is these temperatures are absolute temperatures. They are not in centigrade or Fahrenheit. They have to be in Kelvin or Rankine or some other absolute temperature scale. So TL and TH, absolute scale. In other words, need to be in degrees Kelvin or degrees Rankine. Kelvin or Rankine. Let's do an example. Let's do an example here. Let's say we have a heat engine. Let's say we have a heat engine. And this heat engine is a reversible heat engine. Example. Given reversible, no. Forget reversible, just say heat engine. And I have some temperatures here. Let's see here. We have T high is equal to 555. I'm sorry, 550 degrees C. T low is equal to 25 degrees C. So I got my reservoir temperatures. What do I want to find? Find eta max. The maximum efficiency for my heat engine operating between those two temperature reservoirs. Okay? What's the maximum efficiency? Okay, let's get started here. Whoops. Uh-oh. Sorry about that. Example. Heat engine. High temperature reservoir, 550 degrees. Low temperature reservoir, 25. Find the maximum efficiency, okay? Let's put up a schematic. Let's do that too. So here we have TH at 550 degrees C. We have our low temperature reservoir at 25 degrees C. And I have a heat engine. It's working in a cycle. It's extracting a certain amount of heat Q high, rejecting a certain amount of heat Q low, and producing work over the cycle, okay? I want to know what the maximum efficiency is for that heat engine. What's the maximum efficiency? Okay, well, analysis. Eta max. Well, we know that the most efficient heat engine is a reversible heat engine. That's what we concluded just a moment ago. Eta max is equal to eta reversible. Now, what's the efficiency of my reversible heat engine? Well, from the definition of efficiency, so it's the cycle work divided by the heat input, and this is for a reversible heat engine. Remember, the cycle work is equal to Q high minus Q low, and this is for the reversible heat engine, okay? Oops. Q low, Q high, W over the cycle, apply the energy balance to the heat engine over the cycle, and you get that the cycle work is Q high minus QL. Okay, just from the energy balance. All right? Okay, so Q high divided minus QL divided by Q high, I get 1 minus QL over QH for the reversible heat engine. Now, what is that ratio? That ratio is equal to the temperature ratio of the two reservoirs. QL over QH for a reversible process is equal to TL over TH for a reversible process. A reversible device utilizes a reversible process to produce work. Okay, so let's put that temperature ratio in here. So we got TL over TH. Now these temperatures need to be in Rankine or Kelvin. We have 510 degrees C, that's for T high, and 25 degrees C, that's for T low. So I have 1 minus 25 degrees C plus 273. That's going to be in units of Kelvin. And then I have 550 plus 273, and that's going to be in Kelvin. Notice the Kelvins cancel out. Let's go through and calculate this. So we got 25 plus 273 divided by 550 plus 273. And I get 63%, 0.638, or if you like, 63.8%. The maximum efficiency of any heat engine operating between those two reservoirs, those temperatures, 25 and 550 degrees C, the maximum possible efficiency is 63.8%. As an engineer at General Motors, you better know that. Don't try to make a heat engine, an internal combustion engine, a diesel engine, a gas turbine, any of it. Don't try to make a heat engine with greater efficiency than 63% operating between these two temperature limits, 550 and 25 degrees C, because it is not possible. Maximum efficiency, 63.8%. You could do this problem with a refrigerator and a heat pump. The ratio of the heat transfers, QL over QH, will be equal to TL over TH, and you could calculate the maximum efficiency of an equivalent refrigerator or heat pump operating between these two reservoirs as well. You could easily do this problem with a refrigerator or a heat pump. All right, ladies and gentlemen, I think that's all for today. We'll finish this up next time and move on to more material.